Hi everyone, I'm Livia. Welcome, and today I'm here to interview our Deputy Head of School of Mathematics and Statistics in USW, Professor John Roberts. Hi, Professor John Roberts. It's our pleasure to have such an opportunity to interview today. And the first question is that for the start of our conversation, would you like to introduce yourself in a few words to the audiences?
So obviously I'm John Roberts, although there's 3 or 4 John Roberts at UNSW, so I'm John A.G. Roberts. And as you said, I happen to be Deputy Head of School, but I also do research and I do teaching. So yeah, I do a range of things, and I'm very glad that I get a range of things to do.
And the second question is that, as a researcher, what's your interested field of research? Can you broadly introduce it to us? Maybe also tell us why you are interested in it.
Okay, my particular area of interest is what's called dynamical systems. Sometimes this was popularized in the 90s and it was given the name chaos theory. Some people have heard of this. And basically it's how things change with time. And so of course this started with Isaac Newton thinking about the motion of planets and so on, and how do planets go around the sun and what are the equations for that and can you predict that. And now dynamical systems is a very rich field that goes across physics, mathematics, computer science, biology, and it basically allows you to look at and perhaps predict how things change with time, systems change with time. And I have particular interest in that area, what are called integrable dynamical systems, which are very ordered dynamical systems. They're actually the opposite of chaos, so they're non-chaotic systems. And in the last 10 to 15 years I've become very interested in the intersection of number theory and dynamical systems, which is sometimes called arithmetic dynamics. And that's where your time and your space are discrete, and you might be just giving a rule that allows you to move on the integers, for instance, or a permutation of some subset of the integers.
And we've searched and read one of your recent article, Distribution of Periodic Orbits of the Concerted Frozen Map on Rational Lattices.
Yeah.
And it's pretty hard for me to understand.
Okay.
Would you like to introduce the topic to us?
So this paper is about continuing a line of work we've been doing for some time, and basically it was saying, look at permutations that come from certain well-known dynamical systems. So here's an example here. This is a map of the plane. So in other words, if I give you a point xy, this gives you a new point x prime y prime. And this has been very well studied on the plane R2 of real numbers. However, everything in here could be taken on a finite field. Now, a finite field is the set of integers mod p, where p is a prime. Okay, so 0, 1, 2 is a finite field. Okay, except you've got to do everything, all the multiplications and everything, and divisions have to be done in mod 3. So my collaborator in London and I had done some experiments on permutations that had a certain property, which you see highlighted in red here, called reversible. And we had found that if you go and look at the distribution of the cycle lengths of a permutation, like this, you will find that when it's properly scaled, it turns into this function here, 1 minus e to the minus x, 1 plus x. And so people have to remember something about permutations, and that is that if you have a permutation, it doesn't matter how many integers I have, so a permutation of n objects, you can write down the dynamics of the permutation in terms of cycles. So everything in the permutation comes back to itself under a certain time. So the whole space decomposes into, or partitions into cycles. And each of those cycles has a length. So if you like, what we were saying was, if you go and look at this mod prime, and now let prime p go to infinity, you see I have this, then it was our conjecture that the distribution of the cycle lengths, this is a cumulative distribution, will go to this function. Okay, and here actually is a little, the smooth line here that you see under here is this function, 1 minus e to the minus x, 1 plus x, and the little jagged line is a computer experiment done for prime 997. So you've actually gone and taken p-squared elements, because that's how many you do have in this set. You've taken the permutation, which is induced by this rule, and you've gone and calculated all the cycles, and then you've set up a scaling, and what I'm showing you is that numerically this looks very much like this function. So it raised the question, what's the simplest type of dynamical system or permutation where we can still recover that? And that's what was happening with this Casati-Prozin map. It's a map of a permutation of actually what we call a lattice living on a torus. And we went and calculated the distribution for this Casati-Prozin map. That's what CPM stands for. It has 2 parameters in it, so we did it for all parameters, and we compared the distribution that you found, and we compared its distance. This is a sort of a norm here. This is a thing that tells you the distance from that function r of x that I showed you. And the results can sort of be viewed in this heat map. So this is a picture which is showing you the whole parameter space, or it's actually half the parameter space. So every pixel here represents choosing parameters in the map equal to where the pixel is, then running that permutation, calculating all the cycles, and then checking how different is the distribution to our conjecture. And so here's the map, heat map over here. Blue means good. That means for these parameter values, our conjecture looks very good. And then you see there are some hot spots where the conjecture doesn't work. You see there's green and red here. If you look very carefully, there's some red up here and some red down here. And if you look even more carefully, you'll see there's a red line here. So this is, and that's a blow up where you start to see this gradation of colour. And so the idea is that there are places where you're not getting that distribution. And then we came up with a nice way of breaking up the parameter space. And we made a conjecture that this was the distribution. And if you look at the way this is written down, and if you understand the mathematics, that is a fancy way of writing down something that is a step distribution. Okay, and so the idea is that we checked with these functions that if you now let the number of steps go to infinity, then sure enough, in the limit that k goes to infinity, this goes to that distribution that I showed you. So this is, again, a construction that again suggests that this distribution r of x is recovered from the Casati-Prozin map, but also we know the way it's recovered because we can see the limit of these step distributions.
And could you give some suggestions to the current students who want to do research on maps?
Well, yes, do it. Because we have to correct this idea that many of us experience at school that make maths look dull and boring. Maths is very alive. It's a language that allows you to now virtually do any science, and it's used in every science and engineering. But to me, as well as being an enabler or a facilitator, maths to me is as beautiful as music or art. And I think somehow that message doesn't get transmitted to enough kids at school. And so I would say, go for it. Do enough maths until you can see how beautiful it is. You will always be able to use it, and it will train your brain to think in a very useful way. And a lot of employers say they love people with maths backgrounds because they're very good at problem solving. And most jobs at some level are about problem solving. So, of course, I'm not going to say the opposite. I'm not going to say don't do research, but I think we need a lot more people who do research in maths and discover how beautiful mathematics is.
And thank you for giving us those suggestions. Yeah, that's all of our interview. Thank you for sharing your story and your advice to us, Professor Robs, and hope you enjoy the time.
It's a pleasure. Thank you. I have.